I think we can go ahead and get started. Welcome to the breakout session on material flammability and habitat fire safety. We've had, some presentations in the plenary and then the concurrent sessions that have covered aspects of this. So now we want to dive a little bit deeper into gaps and needs and what we can do. I mean, the co-facilitators for this, myself, Gary Ruff, and Dr. Paul Verkool, and the note takers are Dr. Sandra Olson and Dr. Michael Johnston. This is just so that we can facilitate a discussion. You don't have to go on to onto video. Don't want any impediments to or hesitation to expressing an opinion. The goal of this breakout session is to obtain science community input on priority lunar fundamental and physical sciences, technology and capability needs and collaborations. This was what Craig Kundrat was talking about today and earlier today, and how they'll use this information. Want to make sure that you recognize gaps exist not only in spacecraft and habitat fire safety, but we're also interested in combustion science, at which the for which the moon is a new and valuable laboratory. So the objectives are there really questions, formulating questions, I guess. What are the top priority physical sciences knowledge gaps and research topics that must be conducted on the moon to enable sustained lunar habitation and future Mars missions, and then asking about some of the time frame, what meaningful science can be conducted on the moon given its unique environment, key technologies, technical capabilities and resources needed to conduct physical science research or combustion fire safety research on Gateway and the moon, and then are there useful collaborations that we really haven't taken advantage of. Just to start off with some of the gaps, there's really two kinds here, and I wanted to start by showing some of this. The capability gaps for exploration. The Human Exploration and Operations Mission Directorate sanctions the SCLTs, or the System Capability Leadership Teams, to identify what those gaps are. And these are capability gaps, and you can kind of see the environmental control and life support systems. These are the main areas that the ECLS SCLT covers, and that's where fire safety is, where as part of that ECLS organization. And this slide really shows the identified the gaps for fire safety that is tracked by this this group or identified. There's 8 that are associated with aspects of fire safety, and that some of it we've talked about. It goes into from clothing for enriched oxygen atmospheres, fire safety training, which is really just trying to make sure that the crew is well trained in not just how to operate an extinguisher, but how to respond and suppress a fire in low G or partial gravity. Material flammability and fire propagation in low and partial gravity environments and at the exploration atmospheres, looking at fire detection, suppression, and post-fire monitoring. One of the detailed post-fire gaps is a fire emergency breathing mask. Non-flammable materials, additives, and coatings is one of the gaps that really is going to be necessary to go to the higher oxygen concentrations that we that we need. And then lastly, it's written as a fire emergency test area, but it's really all of the data, the process that you used, to conduct the tests and to really certify any kind of fire safety response equipment. So that's the kind of thing that the SCLT has identified as an exploration gap. And one of the things that we wanted to do was to try to discuss other gaps that must be addressed for fire safety of lunar landers and habitats. And don't forget, though, we also want to look at combustion science investigations. What research topics are particularly relevant for study on the moon. We want to look at the type of facility or facilities that would be needed to conduct combustion research, normal things like mass, power, and volume diagnostics and crew interaction. But then again, also, what collaborations might be necessary to do that. One of these other, as far as facility or facilities, it's more of what do we, or also what limitations would we have on the moon for what we can do? And some of this was covered in the life support sessions about, we would want to vent combustion products after some cleanup, but how much do you have to clean up before you would vent on the moon? And then what's the fate of whatever it is you're venting after it gets there? So really, that was just a lead in to this breakout session. And we can go back and explain or discuss in more detail any of the gaps that I shown there, that I showed before. But what we're really looking at are what are the top priority physical science knowledge gaps and research topics that must be conducted. I think we've seen the just the material flammability and flammability limits and the needs for that. What about other areas in like fire detection?
I guess I have a question. This is Tom Orlando from Georgia Tech. I work with Sarah. Our philosophy is try to do detection of a fire before it happens, so that you can have prognostics and sort of real-time decision making. So that's something that's within the home STRI philosophy. Does that generally fit into the philosophy here? That would be fire prevention, but correlated with some overheating event or something that didn't quite get to the fire point.
Yes, others can jump into this too, but yes, that is a early fire detection and detection of fire signatures, or even overheating signatures would be something that is useful. I think one of the things that gets into use there is the complexity of the system, where you have to sample from, and how many of these units, normally a spacecraft will have more than one detector. So how many do you need to protect any given volume?
Yeah, so that's a good question. So this is going to be predicated on a distributed network, to address exactly what you said. So that'll be dependent upon what the architecture and structure of the habitat is. But it would require a distributed network and a constant feedback process where there was information exchange between nodes.
Okay.
So what knowledge
and
gaps do you associate with that?
well, actually, the knowledge gap, one of the knowledge gaps associated with it is what is the response function? How is it going to be? Will if it's on an autonomously controlled vehicle, will the vehicle respond itself, or is there some robotic response, or if there's humans there, is there some human intervention? So that's sort of the end point of a knowledge, sort of an operational gap. I think part of the knowledge gap is how indicative, how specific can you do a chemical detection and then correlate it with a fault or a fault that could lead to fire. And then which faults are sort of normal under, just for the sake of an example, under ISS conditions. The CO and CO2 levels will go up when there's a fire, but they can also go up when your scrubbers don't work, right? And so, what drives fault conditions, I think, is important, in the role of fire and driving a fault versus some other off normal or some normal event, maybe, or off normal event.
Well, that's a good point, because just running any specific type of equipment could, have a signature for species. Do you expect that some of these signatures and things that you're looking for would be different just because of the lunar gravity?
That's a very good question. If the combustion event will be changed by lunar gravity, the thermal, the thermal properties of the material and then the volatile release rates may be affected by it. We've seen absolutely zero in the literature on that topic.
Well, there's also, this is Phoebe Kelly Serrato. There's also other anomalous dust particles that smoke detectors can also mistake for flammability too, and you have to consider that in the mix as well.
Yeah, this is Claire Fortenberry. To Phoebe's point, I think that I was able to catch Sarah's talk, and I think you guys have a good. I think that smoke detection has kind of relied on detection of smoke particles for several reasons. One thing that has been, I think, talked about to address the problem of potential false alarms is to have like a couple of sensors kind of in tandem. So do you have these different detection methods to detect the different kinds of materials, and can you suss out whether it's lunar dust versus a smoke particle? The other, I guess, question I had for Tom and Sarah is, or larger point with overheating materials, is how much the chemical composition of the products can, as well as the particle properties, so the size and the composition, that really can vary depending on the heating method as well. So I don't know if y'all have been testing like different types of heating methods. I know that was one big takeaway from the same experiments that were done in microgravity, is that like it can be really challenging to, I guess, get something that's repeatable and to account for all potential fire scenarios, because they can produce such different products.
Sarah is on. If she's on, I would let her answer this, because this is her thesis work. If she's not, I can give you a comment.
Yes, I'm on.
Yeah, so that's a great question. And we have kind of looked at um, maybe a limited range of conditions in which these fires happen, because we've been specifically looking at kind of regular Earth gravity situations. So I think there is a lot of potential there to investigate other conditions and kind of like other fire conditions, because I think I know what you're talking about with the same studies. So yeah, I think there's some interest in knowing the different ways that we can expect overheating to occur, and how that can, and I think that would maybe affect some of the situations we're studying.
Yeah, and we're looking at very small sizes just for, sort of practical purposes, so that she can get a good lab measurement to map to the machine learning. But we would like to be able to do some things and get some empirical scaling parameters so that we can address what you brought up, because the volatile release will be heavily dependent upon the size, the composition, and the heat. And we'll try and get as much data on that as we can. And there's where the machine learning and sort of more complex analysis will come out, as it could give us some predictive outputs as well. But yeah, so that's a very important point, and that is I would say that's a knowledge gap, is how do these things behave, even pre-combustion.
Yeah, for sure. I guess my other another point that I'd thought of, one thing that, again, smoke detection is relied on detection of particles rather than gases, and I guess maybe a gap in instrumentation is if you're getting very, are you guys, what I guess thinking about the concentrations of gases that you're getting when you have it in sort of a volume that's big and well mixed. I guess my thought is, when you start to consider times to alarm, that can, I think, get to be quite long with VOCs, but also with particles, with the filtration. So I guess another gap I would say, I would really emphasize, is that with these materials, as you're sort of looking at the different scenarios and you're looking at the different chemical signatures, I think something that's going to be important is defining, I guess, an emission factor. So, how much of this product are you producing per, mass of fuel, such that, that can be taken to model to models to say, okay, well, we know that the volume has, that the eclipse has like these different conditions, and, are we going to reach the alarm threshold in a timely fashion? So that's just another thing that I'd thought of.
So that's very important, and this is something that we're struggling with, is to, we have to set a discrimination level as to what's an alarming level. So the mass spec is very, very sensitive. It could get parts per trillion levels, right? But that everything's going to be there at that level, and so you don't want that to be your trigger. So that's something we don't know, is what is the discrimination level for any for particular materials, and then have it at a network or an overlapping sensor array, so that you don't have just one trigger and give you a false alarm. There has to be some synchronous faults. But we do not actually look at particles specifically. This is completely based on VOCs at the moment.
This
And-
is sorry.
No, please
This-
go ahead.
This is Xiaoliang Wang from DRI. My understanding is the International Space Station already have a mass spec on board. Have anyone been looking at the fire signatures from the mass spec?
So we know this group, and we work with them a little bit. I may be mistaken, but they have a GCMS on there, and they do some basically collection of materials. So the time constant on that is a little bit slow. This one here is more like a real-time monitor, and it's on constantly. I may be incorrect with regard to whether or not they still operated it in GC mode, but the one that I'm aware of is that way.
What sorts of collection methods are you looking at for the mass spec? Is it, it looked like it was a pretty fast time resolution.
Sarah, you want to tell them more about
So the mass spec that we eventually plan to use for this system is able to take scans every 85 milliseconds, and it would be collecting through kind of like a differential pumping system into directly into the mass spec to analyze air samples. And so kind of volume in the sampling system is a little bit in the works right now, but eventually it would be able to collect straight from like the environment it's monitoring.
Does anybody know if a mass spec is planned for like Gateway or any of the or a habitat?
So we participated with a Gateway planning meeting. My colleague Bill Farrell at Goddard, he presented that as a real wish list from an instrumentation point of view, because it could also serve multiple purposes. It could be monitoring volatiles that are on the space station, and it can also be used to look at ion densities and do some plasma diagnostics, and to have some science mission goals too at the same time. But I don't know where that, how well received that concept was, of whether or not it would be, incorporated into the Gateway or not. It would be really good to have, because you can also do a lot of volatile release measurements of samples that you would be, retrieving, and do a lot of real-time analysis of the materials, and maybe circumvent a lot of the uncertainties you would get in sample transfer and treatment back to Earth. We thought it would be a very good, research instrument to have on board.
Okay, might come down to of just, well, who else wants one? If one group or a small group of people would like that instrument, that may have less weight than if you get a whole community wanting to have that capability.
Yeah, sure. Yeah.
Gary, I would say, just looking at the chat, there was a question about could fire alarms be based on visual imaging? I guess I'll take a shot. Somebody can join in. We know that like thermal cameras can be useful to detect hidden fires and so on. I'm not sure how much of the work that Tom has done in signatures has looked at that. Have you looked at any visual imaging, either thermal or otherwise?
That's an interesting comment. That's a really good idea, because we do measurement of the sample temperature with the thermocouple, but there's absolutely no reason why we couldn't do some visual imaging of the of the temperature and do some correlation. Yeah, that's really, that's an interesting suggestion, because there's, really simple handheld imaging devices you can get to get, really good information quickly. I mean, that's how we do, frankly, that's how we diagnose, failed resistors on circuit boards. It's the first point of defense is point this thing at it and see what's hot. And there it is.
Right.
Right. That's a great suggestion.
But there you at least know where to point.
Yeah. There it is. That's a big advantage. Yeah.
And I would think you'd have the same kind of an issue for, knowing what a threshold really is. I mean, with the you almost need a baseline, because with reduced convection, instruments, equipment, could run hotter or run at different temperatures than what they normally did, like when they were being tested on Earth.
Right. Yeah.
So
I
it's
could
just
imagine
knowing what they are.
having a camera like a staring camera, just looking at a scene, and then there'd be a baseline that the camera would learn that this is a normal, and anything out of the ordinary, we maybe flag something that would pop up.
Right.
No, that's a really good idea. And then you can move your camera around. You could scan a lot of different areas. Yeah, that's a great idea.
And also the chat question from Mike Johnston: as we identify these knowledge gaps, I encourage anybody has possible objective or how to fill the gap. Of course, feel free to chime in how we would address some of these practically.
Especially if tests need to be done actually on the lunar surface, we should identify what kind of tests should be done there.
That was kind of going into the one question I had is would we consider a knowledge gap to be, do we even have like a standard way to test a material or a volume? See, I would imagine if you're concerned about a particular material or class of materials, you would have a standard volume and amount of material that you burn in some standard fashion. Is that even, I guess I'm just ignorant, is there something like that that's done now, or is it something that we should consider a gap?
Was this to burn now to get the VOCs? Is that what you're?
Well, just to like you were talking about earlier, Tom mentioned the determining thresholds is never easy, and Claire said that as well. So is there like, just a standard way to, if we want to try to determine a signature, do we have a standard way of setting up that particular test, or do we, just here's a plastic, we want to put it in this size volume and overheat it at this rate, and then see what the signature is, or is it just sort of a ad hoc, more open-ended in terms of determining fire signatures for a particular case?
I know they had the 6001 off-gassing test for a while. I guess it doesn't answer this question on whether they calibrate their sensors with a known supply, like you were implying, though.
I think the answer is ultimately our is going to be dependent on your vehicle, volume, and how it's being used. So unlike terrestrial applications where there's a standard detector sensitivity, it really depends on how big your vehicle is. If it's vehicle is a lot smaller, you have a lot less tolerance for fire than if it's a big thing like a space station. So
you have to build a database of what molecules, how much you're detecting, though, and then you could scale it, I suppose. But if you don't even know what wire insulation is giving off, then you really can't do anything with your detector.
Right. So within that fire, separately, we're proposing a fire certification process rather than a prescriptive process where someone to certify their spacecraft would have to say, I can detect a fire in time to put it out before people die or get hurt. And so it really is going to scale with your spacecraft.
So what is the proposed fire suppression technique used in space in lunar habitat?
We don't know. We haven't been.
It's probably not going to be doused with water. That'll be unlikely, given the amount of water there.
Water on fire.
I don't know.
That sounds like a gap.
Gateway, I think that a water spray is, baseline for that vehicle.
Yeah, even though it is a precious commodity, I think there's some cases where you just have to use it potentially in a fire extinguisher. Another option might be to use like fire blankets and stuff.
And the water would be recoverable too, so potentially.
Well, certainly, you got to get out of the air. So but whether you can reload your extinguisher.
Is there anything else that you'd want to use as a extinguishing agent that would be?
Sandy suggests fire blankets in the chat.
Well,
yeah,
there might be the question whether you have a second room which is not on fire and evacuate the room with fire, the oxygen, the atmosphere out of it. Would that get you to something?
Yeah, I think having an airlock system could be useful, certainly.
Yeah, some kind of safety room, especially for that, which is more or less fireproof, and getting the crew evacuated into that room and evacuate all the oxygen from the rest of the station.
Mm-hmm.
Just an idea. No air, no oxygen, no fire.
Yeah, that seems to be a reasonable thing, especially if you reach dire situation where it's really out of hand, you have no other options left. That might be the last resource, but it's something that should be considered. I'm sure it will be, to have a safe, self-contained, isolated chamber.
That could also be just a precautionary method because you have probably enough EVA suits for everyone that's in there now. You could just get out and dump the oxygen.
Yeah, you don't have time. Time to don a spacesuit is long compared to time for a fire. Contrary to movie Aliens, where
it depends on the suit.
Yeah, current designs. Still need your
another suggestion, a kind of spray that builds up something like a kind of bubble structure, which is removable easily from the surface again, but in the moment of the fire, that it's getting the thing closed to a certain area, so that there is no additional oxygen getting there.
So you're talking like
it must be fireproof instead of a blanket.
So like a spray blanket almost, or spray foam that would condense and make a blanket, right?
Yeah.
And I know I saw a situation once where there was like this lightweight foam that just covered somebody, and then it broke away after the fire was over.
Must be easily removable again, of course.
Yeah, of course, it's removable.
Yeah.
What kind of foam is that?
I don't know what kind of foam it was. I just know that it sprayed, it released, when the fire was combusting and covered the person, and then they broke. I just saw it in a film somewhere. I don't know what it was. It was interesting though.
Huh. So it was a rigid foam that you said it set.
Yeah, it's set, but it left room around the person's face so they could breathe until they could release them from the foam, which was really interesting. I saw it in a safety film somewhere, and I can't remember where I saw it, but it was kind of interesting. And it was described as a lightweight film because they just cracked it and removed them. It was like a cocoon that enveloped them.
The
Interesting.
Another idea might be you have always a van going on in the station to get the airflow around and having no areas with high CO2 part. So if you simply also stop in that situation all the fanning of the air so that it comes to a stop.
Yeah, but wouldn't that suck all the breathable air out of the environment and leave the crew without anything to breathe?
No, not just in the area in the module, which you got the problem to stop the air around the airflow. The air is still inside, but to stop the airflow so that on the certain spot.
Just fire, the moving air, just the moving air is what you're
talking about. The moving of
about.
the air, exactly. Yes,
okay.
Ma'am. Yeah, and so that the oxygen is burned up, and so maybe it's a possibility to get it lower. I don't know, but might be.
Well, that's a thought.
That's what they do in the ISS, but in the partial gravity, you'll have buoyant flow, so you can't get rid of it.
That's true, but in Gateway, for example.
Yeah, that's currently the approach for like on the ISS, and I expect it'll be the same on the Gateway.
So I think I'd go back to, we've kind of talked some about, detection and different suppression methods, but then, items 2 and 3 on these objectives, what kind of tests and test facilities would you want to use to, figure some of this out? Whether it's the, VOC signatures, or some of the other fire detection methods that we discussed.
Well, the question to ask is, what kind of fire detection testing environments do you currently have that you're using to actually conduct these tests at present? What's presently available now? And then from there, determine what you actually need and what you actually want to conduct more tests. Those are the two questions you need to determine.
I think that's a good point. For example, we use the standard test on Earth, a 6001 test, where we just basically burn single samples and see if they go out or not. So that would entail having essentially a chamber that we could do these tests on and then do many of them. So this would be something that I can't envision doing initially because of the other constraints on the occupant's time in terms of doing lots of flammability tests. But at some point, it would be nice to have either a chamber or a glove box, I think, on the moon, so that we can do, we and the inhabitants can do local isolated tests in a isolated environment with certain parameters that can be controlled, and then multiple tests could be done. So I think that would be very useful.
Okay, and is that what you want, or is that what's needed?
Well, I thought your question was what we currently have, and again, what we currently have.
So that's what you currently have. Okay.
Yeah. So that would be something that it works well on Earth for testing fuel samples, many different fuel samples, but of course the limitation is it has to be inside a chamber generally for containment of combustion atmosphere and changing the atmosphere. So yeah, to answer your question, yes, I would want that, but I think it would be a challenge for logistics to do this, to do any tests, but unless we could think of another way, and we are thinking of other ways to do flammability testing. Maybe this is a good time to revisit like some of the tough stuff that Sandy Olson has done to determine flammability in other ways. But that would be like a separate direction. Yeah. So yeah, I would like to do what we currently do, having a separate test and do lots of burns. I'm not sure if practically that makes sense from the beginning.
Well, what you want is one thing, and then what's possible is quite another, so that's why I'm asking the question, just to try to open up, people's minds to see what's actually possible, and also what's doable, with any cost constraints that, might exist.
Yeah, absolutely.
I hope that helps.
Is there a possibility to have some of the instruments or technical things outside of the pressurized module, so that they're in the vacuum of the moon, so that from that point of view, if something with this part of mechanism happens, it would be outside and not dangerous for the crew inside of a habitat.
I think that is a good point, and they probably will do that.
Yeah, I agree. There could be use for that. Again, since we're going now to a place with gravity, I think it's safe to think to some degree how we do things on Earth. So if you envision a test on Earth in a combustion chamber, normally you can do that.
Yeah, this was just an idea of the way of constructing your habitat, so that you have all the important parts inside of the pressure chamber. Pressure chamber, I mean inside the habitat where you've got your astronauts, and all what is possible to have it outside, out of in the environment of the vacuum of the moon, so that if there is something overheating and getting a problem, that there would be a breakdown of this part of instrumentation or whatever it is, but it won't lead into a fire inside of the habitat. This is what I meant. Sorry for my not so perfect English.
No, we understand completely. It makes sense. I think, if I could paraphrase, I think that the things that we consider to be very dangerous or potentially unsafe should be done in an isolated environment or like you said, a separate construction. So that certainly makes sense. So the question then becomes is, would we assess, how do we determine what is excessively dangerous for it to need to be done in a separate habitat or separate enclosure? So that's, I guess, just a optimization or a prioritization of how dangerous could it potentially be. But it is certainly something that should be considered.
Well, as a safety engineer, I start thinking of, the criticality of, starting to break it down into danger zones, outside the habitat versus inside the habitat. And I certainly see what he's saying there. That totally makes sense to me. Yeah, I get that.
You had well, I'm a museums man. Yeah, I'm the curator of the Hermann Oberth Spaceflight Museum in Germany. So I'm looking always to those questions from a point from history. And you had all this kind. I don't know what 6001 is. I think it's a standard of checking flammable things in the environment of a certain kind of chamber with different kinds of atmosphere. You have talked before, or I have heard before, the different types of atmospheres which are planned for different types of in the spacesuit, and also around in the gateway, and also on the lunar surface in the habitats. Of course, the first question is out of the gravity, how things may burn in this special environment. Those tests are of course necessary, and maybe those little tests can be done even on ISS on a small scale in a little kind of centrifuge to get the same environment, but with a sixth of a G maybe, because the movement, of course, it should be great to have, but maybe there is a possibility to do it that way.
Yeah, there have been efforts to get a centrifuge on the station, but it's always bumped into cost and vibration issues. But
yes, of course.
It's a great idea, certainly. I mean, it would be one way to do that. We've done similar stuff at strictly 0G with a flow. We've done lots and lots of tests in the microgravity glove box to have a facility that rotates and generates, sub-Earth gravity. We could do quick and dirty, or lots of tests, I should say, of different fuel samples, and that would be wonderful. But as David said, it's always a matter of as money and budget and time, of course. And
maybe you also can do it with a sounding rocket. You just need a little test. Maybe this is quite sufficient in those short moments, and this might be cheaper than get it to the space station, of course.
You're reading our minds. We're pursuing that with a sounding rocket test with a rotating capsule. So
sorry for that. I'm not a mind reader.
Yeah, but that's good. We're actually doing that we're working with Blue Origin to have they're going to rotate the entire capsule in the sounding rocket test. So we're actually going to burn things. So that's certainly you're definitely thinking like we are.
I'm lucky about that. I'm happy about that.
Yeah, we'd hope to do drop tower studies at partial G. In Hanover, they hope to have their Einstein elevator produce partial G testing. We hope to have a similar facility in the U.S. eventually.
But what easily could be done, in my mind, to have those different materials in a test, how much compared to Earth from the heat from the material will turn over in the certified kind of atmosphere you use in the different in the different habitats or environments. Because the material we use on Earth, it's in Earth atmosphere, and compared to that, there is radiation into the air and so on. And if this will be tested under the circumstances of the atmosphere and the pressure inside of the module in a little test chamber, then we have first indications of the behavior of this material when it's getting too hot. How much is getting off it? Or do we need drips or stuff like that, a broader area, so that it, or even a cooling system, so that it's get rid of the potential overheating?
So actually, that is the philosophy of Sarah's thesis. That whole paradigm is defined, except for we can't do anything with reduced gravity.
Yeah.
And so, so the question, I guess, I kind of put it in the chat. We're designing this cube, this mass spectrometer, so that it could be in a CubeSat. So this is going to be, fairly small footprint, and it'll be self-contained in a box where you can control the pressure and the background gas composition. We never tried to put something on the ISS, so I have no idea on how complicated it would be to get something like that on the ISS. But if we could do that, then we would do Earth-based measurements and then compare them under identical experimental conditions, except for we have it on the ISS, where the reduced gravity component is now appropriately covered.
Well, if it's a 80 millisecond response time, I think I heard you guys say, is that something that should be done in a drop tower that has 5.2 seconds available?
Yeah, okay, that's a good, maybe easier. Yeah, shared. Yeah, we should talk to people who do the dropout tower stuff. That would be interesting for sure.
I think you are.
Yeah. Yeah, I mean more directly beyond this, big open forum here.
It does survive 60 Gs though of deceleration.
Yeah. Did any one of you have ever looked in the parabola flights if you can have, instead of 0G, also a 6G environment for the time of the drop of the aircraft?
Yeah, so Professor Tian presented some results on that, and it certainly is possible. Sixth or third or virtually any G level. It's just subject to the accuracy of the pilots and the normal turbulence you're used to when you fly.
Yeah, because if he could do something like that, to have this 6-tree, all the other rest, what we need, could be done inside of the aircraft by experimentators who control the experiment and even can see it. So we would have this not 0G, but exactly what we got on the moon. And this would be the right environment to have, of course, having a controlled a little fire in an aircraft is something what you don't want to have. But this would be maybe the possibility to have a 6 of a G. Lunar gravity.
Yeah, it's feasible. It's done. The trick is, can you tolerate the G quality for your experiment? And
yeah.
But certainly it was very important for our flammability research because it was the earliest access we had to partial G before Paul built the centrifuge.
Just an idea.
And ESA is a nice aircraft they use to do that.
Okay, I think we are getting close to a scheduled break time.
Oh, I guess so.
Yeah, you're right. So theoretically, a 10-minute break for people to cover, and then it starts up again at 3:30 Eastern.
Yeah, we'll start up and think of some other questions or topics. One of the things that I'd like to make sure that we hit on is any other kind of fundamental combustion science that would be made possible on the moon, or where there's a particular where that particular environment could be useful, or maybe help to fill out a data set between 1G, 0G, and Lunar G. So we'll adjourn here for 10 minutes and come back at 3:30.